Hello and welcome to the 15th lecture of the machining science course. So, in the previous lecture we started discussing the grinding process, abrasive machining process, and we said that the basic grinding process is the basic abrasive machining process is the grinding, and there are 5 factors on which the performance of the grinding will depend. It is the type of the abrasive material, this is the grain size, third is the grade, fourth is the structure, and then the bonding material. And the grinding wheel specified by these 5 factors, that is the abrasive size in the first, then the abrasive type of abrasive first, then the abrasive size, then the grade, then the structure, and then the bond. Now, let us see different kind of grinding processes. So, basically in the grinding we can grind the flat surfaces, and here these are the examples of the horizontal surface grinding where you are getting the flat surfaces. And as I said that if the axis of the grinding wheel is horizontal, it is called the horizontal surface grinding. These are the figures. And if the axis is vertical, these are called the vertical surface grinding. The vertical surface grinding, here it can also have a cup type of grinding wheel. So, here it rotates and the workpiece also rotates, all right. So, in this case, for example, here we are getting the flat surface as well as in this case. Whereas, this is the example of the cylindrical grinding. It can be either external cylindrical grinding, this is the wheel, and this is the workpiece where we are getting the external surface ground, or it can be an internal cylindrical grinding where this is the grinding wheel and the internal surface of the workpiece is getting ground. This is the example of the in a better picture of, let us say, cylindrical grinding. This is the external cylindrical grinding and this is the internal cylindrical grinding. So, this is the grinding wheel which rotates with respect to the workpiece, and the workpiece also rotates at an opposite direction, and the grinding wheel is reciprocates along the axis of the workpiece. So, these are the movements or the motions which are given to the process. Now, this is a very typical grinding process which is called the centerless grinding process, and here the schematically it is shown here. This is the workpiece, this is the grinding wheel. There is a supporting wheel which supports the workpiece in the sense that it actually controls the outer speed of the workpiece. The peripheral speed of the workpiece is controlled by the rotating wheel, and the rotating wheel is located at an angle with respect to the workpiece and the grinding wheel. If you see the side view will be like this. So, let us say this is the axis of the supporting wheel, this axis is already shown here. So, this is the axis of the supporting wheel, and this axis is tilted with respect to the axis of the grinding wheel. This is the axis of the grinding wheel. It is at an angle of around 3 to 5 degree, okay, very small angle. So, this is given, this is the axis of the wheel of the grinding wheel, and this is the axis of the regulating wheel. They are making an angle of 3 to 5 degree. So, this is particularly given so that the workpiece, which is not held by anything, but this is supported just by a knife, or which is called the rest blade, all right. It is neither supported by a 3-jaw chuck or centers like in the case of the other grinding processes or a magnetic table, for example, but here it is only held by the rest blade, sometimes it is called the knife, and the outer peripheral velocity of the workpiece is regulated by the regulating wheel, as well as it gives a feed in this direction, okay, because the regulating wheel is inclined with respect to the grinding wheel. So, suppose if the during the process, here is that force which is W r and the dr by 2. Okay. So, dr by 2. So, this will be the at feed velocity will be W r d r by 2 and the sine of this, let us say this is theta, okay, sine theta. So, this is the speed at which the workpiece will be fed, because workpiece has to be fed. In this case the workpiece is very thin, okay. These are the let us say long needles, okay, and they are very fragile, they cannot be ground otherwise, they cannot be made as a external cylindrical grinding. So, therefore, in this case this is the process which is used, and long needles they are used for example as bearing element, okay. So, needle bearing you must have heard, which are used as thrust bearings. So, needles are those bearing elements which are ground using this centerless grinding process. And it is a very effective process, very quick, and it makes a it gives a good surface of the needle without bending or buckling of the needle, because in all other processes needle cannot be ground otherwise. Okay. This is the grinding machine and the grinding process is shown. This is overall, this is the pictorial view. Now, here one thing that I should tell you, that you will see the grinding machine before the grinding process starts, it has to be covered, because the speed of the grinding wheel, I told you once that this is about 10 to 80 meter per minute, sorry, meter per second, and Vf, that is the feed velocity, whereas this is about 0.5, 0.6 meter per second. So, you can see that this velocity, cutting velocity, okay, is very high, and at this velocity if anything breaks, any point, any part of the grinding wheel breaks, it will be like a bullet. So, it will always be covered by a wheel guard, and the wheel has to be properly balanced, particularly for the bigger wheels, before it actually starts grinding, because of the same reason, because it is rotating at a very high speed, and without balancing, if we are using the grinding wheel, in that case the grinding wheel can break. Now, let us see the mechanics of grinding process and why we should learn the mechanics. This will give, like in the case of the turning, we have seen the mechanics of machining. Here the mechanics of grinding process gives us the knowledge of how to control the grinding process, okay, and to improve the grinding process overall. So, let us say this is the one grain that we have shown here, and see the grinding wheel is here consisting of many such grains. So, one grain is taken as an example. This grain is removing this much material, all right. So, this is the radius or the diameter by 2, this is the axis of the center of the grinding wheel. So, therefore, from here to here it is also d by 2, which is here d by 2, because this is the diameter of the grinding wheel. Now, if you see one grain, that grain will look like this. Like in case of milling, here also the T1 varies from 0 to maximum. Okay. So, therefore, here we are saying that the T1 is maximum in this space. This needs no explanation, because we have explained that in case of milling, when we were discussing milling. So, this is the depth of cut, this is the feed velocity, okay, and at this velocity the grinding wheel is rotating. From here to here, this is the length of the grinding chip which is being made. If you look at the chip here, so this will be the maximum width and this distance will be the maximum thickness, chip thickness. Now, there is a concept of grinding ratio. That grinding ratio is given by the ratio of B max divided by half of this T1 max. In practice, normally it is between 10 and 20 roughly, okay, in practice. So, the volume of a chip, if this is the chip of a grinding process, the volume of a chip will be half of B max into T1 max and multiplied by the length. This is the length of the chip, all right, chip length. So, B max, half of the B max, since it is assumed to be a triangular, half of the B max into T1 max into L will be the volume of a chip. Now, if you put the value of the gamma g, which is the grinding ratio, B max by 1 by 2 T max here. So, it will be equal to 1 by 4 T 1 T, this is the T 1, T 1 okay, it is already given, T 1 max square into gamma g into L. So, here we are putting the value of the gamma g. This is L is the average chip length, D is the depth of cut, capital D is the grinding wheel diameter, and the B is the width of cut. Okay. Now, the average length of a chip is given by D by 2 into beta. You look at in here, okay, that the figure is repeated here. So, D by 2 into this small angle. So, therefore, it can be assumed as the D by 2 into beta, this is equal to the L. Therefore, L can be expressed in terms of beta as L equal to D by 2 into 2 root over D by D, which is root over D into D, all right. So, this beta, because let us see how this can be obtained. Cos beta from this triangle you can find out as equal to this divided by this, D by 2 minus D is this distance, this is D by 2, this is the radius minus the depth of cut divided by this, all right. So, which makes you 1 minus 2 D by D. Sin beta is root over 1 minus cos square beta, which will give you roughly about root over 4 D by D, because this we are ignoring, okay, saying that this is very small for small d square by capital D square. So, we are ignoring that, and it will be roughly about 2 root over small d by capital D. So, beta is equal to or roughly equal to 2 root over d by d, because for small beta sin beta can be assumed to be beta. This we have seen earlier also when we derived the equation for the milling. So, therefore, we are getting that L is equal to root over d into capital D into small d. Now, the volume of chip therefore, will be 1/4 gamma g T 1 maximum square root over d. We are just putting the value of the capital D and the D root over, all right. Now, the volume of material removal per second, which we call as the material removal rate, this will be given by speed into area. You remember earlier we said that the material removal rate is speed into area. Area is the width and the depth of cut, this makes the area, and the speed is the Vf divided by 60, just to make it millimeter cube by second, all right. So, it will be B into D, which is area, and the speed is Vf divided by 60. So, this will be the volume of material removal per second, or which we call normally as the material removal rate. Now, let us see the number of chips produced per second. How many chips will be producing or how many chips will be produced per second, that will depend on first of all the cutting speed, okay, which is given by pi d n by 60. Okay. This is cutting speed equivalent to. Then it will depend on how much is the width of cut. If more width of cut, it will be more number of chips, right. So, therefore, this will be multiplied by B, and another thing that on that the number of chips will depend on is the number of active grains per unit wheel area. This is called the grain concentration C. That means, per unit wheel surface area how many grains are there. More number of grains will give you more number of chips, because each grain is produced. You see here that this is the one grain and one grain is producing this chip. So, next grain will produce another chip and so on. So, more number of grains, active grains participating in the unit area of the wheel, that will be the grain concentration, and on that the number of chips produced per second will depend. So, therefore, overall the number of chips produced per second, this will be given by velocity into B, that is the width, and the grain concentration. Okay. Now, let us see why we have derived this thing. To find out an equation which will be, well, let us tell this way, yeah, here it is written. So, this equation is made, I mean all these factors are determined, that is the average chip length, volume of a chip, volume of material removal and the number of chips produced, because if you see here the number of chips produced per second into the volume of chip, this will be equal to MRR, volume of material removal. This is what exactly we are making here, that the volume of the chip into the number of chips produced, this is equal to the MRR. This is MRR, material removal rate, this is the volume of chips produced, okay, volume, and this is the number of chips, So, volume into volume of a chip into number of chips, this is equal to material removal rate. So, you can write this equation. From here, if you solve this equation, you can find out the value of the T1 maximum. This is maximum uncut thickness, which will be root over 4 Vf root over depth of cut divided by pi d n c. Gamma g is the grinding ratio, root over, this is capital D, please correct it. This will be capital D. Okay, capital D is the diameter of the grinding wheel. So, if you solve this, then you will find the equation of the value of the T1 maximum. Now, the specific, now why we are making that, you understand that in the specific energy we have the T1 maximum. Okay. So, half of T1 maximum will be the this is T1 maximum, half of T1 maximum will be the T1 average. So, therefore, we need to have the T1 maximum value, which is this we found out by equalizing the product of volume and the number of chips with the material removal rate. Now, if we write that UC is U0 T1 average to the power minus 0.4, which is equal to U0 half of T1 maximum to the power minus 0.4, this we have seen earlier. So, the power can be given as Fc into Vc, all right. So, Fc, which is the cutting force, and Vc, which is the cutting velocity, and we are making that 60 into 1000, so that to match the unit, and the power is normally given in watt. So, to match that we are making that 60 into 1000 millimeter and then minute, converting a minute to second and meter to millimeter. So, this will be equal to power, which can be given as UC and the MRR. MRR is the again B and the D, this is the area and the velocity. Okay. So, power is equal to FCVC or UC into MRR. So, we are using this equation. From here we can find out that the Fc is equal to 1000 B into Vf, all right, D into UC and divided by pi dn. This will come here, 60 is getting cancelled. So, once we have found out what is the value of the Fc, Fc is the total tangential force on the wheel, mind it, total tangential force. So, we are actually not very much interested in the total tangential force, but we are more interested on the force per grit. That means, how much force is acting on each of the grits on the grinding wheel. This is because when we know the maximum force which is acting on the grit, then we can have some kind of a control on that, so that the grit can be dislodged. Okay. Particularly the worn out grits. If you remember, we said about the wheel glazing or wheel loading. So, particularly in case of wheel glazing, what happens is the worn out grains do not come out of the grinding surface, because the wheel is very hard. Okay. So, now if we know the cutting force or the average cutting force per grit, then we can have some kind of a control on that force, so that that force can be increased. Let us see how we can do that. So, average force per grit, okay, if this is Fc prime, then it will be Fc, the total tangential force. I will write down that Fc, mind it, this is total tangential force, okay, total tangential force on the wheel. So, this total tangential force is distributed by the number of grains which are actively participating during the cutting process, that is in this space. right. This is the space where this is the place where the cutting process is going on by a grain. So, how many grains are there during the contact with the workpiece? So, that will define that what will be the average force per grit. That means, average force per grit will be the total tangential force distributed by the B into L into C, and B into L into C, this will be the total number of grains actively participating in that cutting zone. Okay. Therefore, the if we put the value of the FC, which is here, and then you divide by B into L into C here. So, B will get cancelled, okay. L will be root over D into D, capital D into small d, this value. So, you put the value of the L, which is root over diameter, okay, grinding wheel diameter and the depth of cut, all right. So, you will get a formula like this, that FC prime, this is proportional to Vf, we are having that Vf here, depth of cut u0 and these factors. Now, why u0 is coming? Because here you have that uc, all right, and this is equal to u0 and the half of T1 max to the power minus 0.4. So, this u0 is coming here, and rest of it, that is half of the T1 maximum, since it is proportional. So, we are not taking the values here like half, we are saying that proportional to T1 max is here. So, this will be Vf to the power 0.5, small d to the power 0.25 as it is shown here, divided by small capital D to the power 0.5, n c gamma g all to the power 0.5 and capital D to the power 0.25, okay, and the entire thing to the power minus 0.4, because this is what we have here. Now, if we see here, this can be simplified, because Vf, this will be Vf to the power minus 0.2 and this is 1. So, it will be 0.8 and so on. You keep on doing that and simplify this. So, altogether finally, you will have the Fc prime, which is the average force per grit. This will be proportional to u0 Vf to the power 0.8 as I pointed out here. Similarly, it will be small d to the power 0.4, gamma g to the power 0.2, n to the power 0.8, C is the grain concentration, which will be to the power 0.8, and the wheel diameter to the power 1.2. Now, this is the equation that we are having from the mechanics of grinding process, because then we can actually analyze this result to find out that if we are increasing n, if we are if we are decreasing, let us say n, if you are decreasing the grain concentration and if you are decreasing the value of the d, that is the diameter of the wheel, we can actually increase the Fc prime, or we can increase the Fc prime by increasing the Vf, increasing the d. Vf is the feed velocity, small d is the depth of cut, or the gamma g we cannot touch, because gamma g is the constant value and u0 is also constant value. So, you increase this, or you decrease n, c and d, then you can increase the Fc prime, which will actually facilitate the dislodging of the grains, particularly the worn out grains from the wheel surface. So, as I was telling you, in that case what happens is that, suppose you have a grinding wheel which is hard and you are grinding the hard workpiece surface. So, as we said that because of the hard workpiece surface, the grains on the grinding wheel surface will be very quickly worn out. Okay. Now, we want the worn out grains to be dislodged, because worn out grains will rub more, it will consume more power, and it is not effectively making the grinding process. So, it will spoil the surface also. Now, to remove the worn out grains, what we need to have the more force acting per grit, and here is how we can manipulate them. that we can actually increase the feed velocity given the particular grinding wheel and a particular workpiece. We can still make the wheel appear to be softer. Let me write down that, making the wheel appear to be softer. Why it is softer? Because the soft wheel, in case of soft wheel, you know that the grains dislodge very quickly, because the wheel is soft, and wheel is soft means the grade is soft. Grade means the strength of the binding material. So, therefore, this is something which is important while manipulating the grinding process and to improve the surface finish of the grinding process, because otherwise what will happen, that if you have a hard wheel and if you have a hard material, in that case the grinding wheel surface will be spoiled, because the grains are not dislodged, and those grains are worn out grains which will be staying in the surface of the grinding wheel and it will not be dislodged. So, this is the process by which we can still make the grinding wheel appear to be softer. Okay. So, once again I will just repeat that this is not a very complicated thing. What we have done is that we found out that the volume of a chip. In finding out the volume of a chip, we have the L, which is the chip length, which we have made as equal to d by 2 into beta, beta being a small angle. So, here we are putting the value of the small l, which is root over d by d, that we found out from the geometry here. Okay. After that, we find out the volume of material removal per second. So, volume of material removal per second, as we said, that this is the MRR, and this is equal to the area and the velocity. Area is the B into D, B is the width. By the way, that width we mean that here it is not shown. Suppose the width of the material is like this. So, this is the width, okay. And this much width is ground, I mean. So, this width and the D, which is here, that is the depth of cut, this will give you the area of cut. B into D, this you can assume to be the area of cut, okay, area of grinding. So, this area into the velocity, which is Vf by 60. So, we are making that for converting minute to second, okay. This will give you the MRR, and then we are finding out the number of chips produced per second. Number of chips produced per second, as I said, will depend on the cutting velocity, okay. On the width, more will be the number of chips, and the grain concentration, which is defined as the number of active grains per unit volume surface area. Here it is given. So, this is also called the concentration of active grains. Therefore, more the concentration of the active grains, more will be the number of chips. So, we did that to make an equation which says that the volume of a chip into the number of chips, this will give you the material removal rate. Here, from here we can find out the T1 maximum, and this T1 maximum is used while finding out the specific energy and the power, all right, because specific energy we said is equal to U0 into half of T1 maximum, because T1 is taken as a T1 average, and the T1 average is T1 half of T1 maximum. So, by doing that we can find out the value of the power and the force finally. So, this force is the total tangential force, from where we are finding out the force per grit, and then the parameters which we are finding out, these are the parameters which we can manipulate to increase the force per grit to dislodge the worn out grains from the wheel surface. That is the importance of the mechanics of grinding. Rest of the things in grinding we will discuss in our next class. Thank you for your attention.